Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. This is the third lecture in section 9.1, and we continue some theorems about the convergence of sequences. We studied two theorems. We mentioned two theorems. If the function has a limit, then the sequence has the same limit. And we also discussed the squeeze theorem for sequences. There are other two theorems important. We use them also to prove whether the sequence is convergent or divergent. The third theorem in the section is this one. If limit of absolute value of an is 0, then limit of an is 0. So an is a sequence, for example, this one, -1 to the power n. If I take absolute value of an, it would be absolute value of -1 to the power n. -1 to the power n, the first term, if you put n1, you get -1. If you put n2, you get 1. So actually this theorem, this sequence is -1, 1, -1, 1, -1, 1, and so on. So the terms are -1 and 1. So if you take the absolute value of the sequence, you get in fact 1. All the terms would be 1. So absolute value of an, if I ask you what is the limit of absolute value of an when n goes to infinity for this sequence, okay, you will say 1. It is not 0. So you cannot apply the theorem if the limit is 1. You only apply the theorem if the limit of the absolute value of an is 0. For example, this sequence. Now, absolute value of an is 1 over n, because the -1 would be 1. And limit of absolute value of an when n goes to infinity would be the limit of 1 over n when n goes to infinity would be 0. We have seen this, 1 over infinity is 0. So now I have the theorem. Limit a absolute value of an is 0. Then the theorem says, then limit the sequence itself is 0. So I conclude from here that limit -1 to the power n over n when n approaches infinity is 0. And this sequence converge to 0, converges to 0, convergence. So the sequence an is convergent. And you can see that this is the sequence -1 to the power n over n. You can see that at 1 it is -1, okay? But at 2 it become what? Half. At 3 it become -1 over 3. At 4 it becomes 1 over 4, -1 over 5. It approaches 0, okay? It will come close to 0 from the right, from up and down, but it approaches 0 at the end. So it converges to 0. So that's the importance of this theorem. Whenever we have -1 to the power n, we use it and check absolute value of an. If it is 0, then the limit of an is 0. If the limit of absolute value of an is not 0, then we have to figure it out. For example, here, this sequence -1 and 1, it oscillates between two numbers. It doesn't approach a single number when n goes to infinity. So this sequence is divergent. Okay. Determine whether the sequence converges or diverges. Some examples, questions about this theorem. If it converges, find the limits. Well, I have an, there is -1 to the power n, so immediately I will check absolute value of an, which is 1 over 2 square root of an, 2 square root of n. What is the limit of n goes to infinity to 1 over 2 square root of n? 1 over infinity, infinity. 1 over infinity, sorry, is 0. Square root of infinity is infinity times 2, so infinity, so 1 over infinity, 0. So the limit of absolute value of n is 0. So by the theorem, the limit of negative 1 to the power n over 2 times square root of n when n goes to infinity is also 0, and the sequence converges to 0. Check this one. Absolute value of an would be n over n plus square root of n. Now the limit of n over n plus square root of n when n goes to infinity, how do we evaluate the limit when n goes to infinity? We take the highest power up, the highest power down. N over n is 1. Limit of 1 is 1. So absolute value of an goes to 1. It doesn't go to 0. So what happens to an? What happens to an? An is negative 1 to the power n plus 1 times this one, times 1. So at the end, an would be positive or negative 1. So in this case, an does not approach a single number. Okay, we can say it oscillates between 1 and negative 1 and say that the sequence is divergent. Okay, because the limit an will go to plus or minus 1. It will not go to single number. So these are the two examples. If you find that absolute value of an goes to 0, then an goes to 0. If you find that absolute value of an does not go to 0, then an would be divergent because it will go to plus or minus whatever number you have here. The last theorem would be this theorem. I think there is another theorem, maybe. We still have two theorems. If limit an is L and the function f is continuous at L, then limit of an is f of L. So in fact, this theorem enables you, gives you a way to find the limit of f of an. How to find the limit of f of an? You write it f of, and you find the limit of an when n goes to infinity. And if you find that the limit of an when n goes to infinity is L, then the limit of f of an would be f of L. Okay, let us illustrate by example. How to find limit sine pi over n? Well, you can immediately write this as sine limit pi over n when n goes to infinity. So f of the limit, okay, you let the limit inside the sign. And now what is limit pi over n when n goes to infinity? Pi is a number over infinity, 0. So I will have sine 0. But what is sine 0? 0. So the limit of this sequence would be 0, and this sequence is converges to 0. Differentiate between sine n, which we had before, and this is sine pi over n. So there is a big difference when n comes in the numerator or in the denominator. Determine whether the sequence converges or diverges. If it converges, find the limits. I have a here. I will start by finding the limit as usual to check convergence or divergence. So limit of e to the power negative 1 over square root of n. Okay. How can I find this limit? I will let the limit in. So it would be e to the limit when n approaches infinity of negative 1 over square root of n. But the limit of negative 1 over square root of n, when you replace n by infinity, square root of infinity is infinity, negative 1 over infinity is 0. So it is e to the power 0 or 1. So this is the limit, and the sequence is convergent. Similar here, to find the limit of an when n goes to infinity, okay, of an, I will let the limit inside the root. I will write it to root of limit when n goes to infinity of 1 plus 4n square over 1 plus n square. And how do we find the limit? We take the highest power. And the term with the highest power in the numerator is 4n square. And the term with the highest power in the denominator is n square. N square cancels with n square, and the limit of 4 is just 4, and square root of 4 is 2, and the sequence is convergent. Similarly, to find the limit of an when n goes to infinity, I let the limit in. So it would be cosine limit when n goes to infinity of n pi over n plus 1. How do we find the limit when n goes to infinity? The highest term with the highest power, term with the highest power, n cancels with n. Limit of pi is pi, so this is cosine pi, and cosine pi is -1. So it is convergent. I will leave this for you. You do it similarly, okay? You find the answer. I will do 50. Find the limit of an when n goes to infinity. So it is the limit of what? I will write it 2 to the power 1 plus 3n over the index. What is the index? The index is n, okay? Because you know when you have the nth root of a to the power m, you write it a to the power m over n. And now it would be 2 to the power limit when n goes to infinity of 1 plus 3n over n. But you take the highest power up in the numerator, which is 3n, the term with the highest power, over n. N cancels with n. Limit of 3 is 3, and 2 to the power 3 is just 8. So this sequence converges. By looking, I tell you here that if you take the limit of 2n over n plus 2, it would be 2n over n, it would be 2. So in fact, an will go to e square. So check that. And it will converge to e to the power 2. It's similar to this question, to 35. The last theorem or fact, the sequence Rn. Rn. R is a number and n is the variable. For example, 2 to the power n, okay? -3, this sequence. -3 to the power n, okay? Half to the power n. -1 over 4 to the power n. All of these sequences are in the form r to the power n. But here r is 2, it's greater than 1. Here r is -3, it is less than -1. Here r is half. Here r is -1 over 4. So r here is between -1 and 1 in these two cases. So here the sequence is convergent, okay? Because when you take the limit, it would be 1 over 2 to the power n. So it would be 1 over infinity, it would be 0. So if r is between -1 and 1, the sequence Rn would be convergent. Otherwise, it would be divergent. So the limit of Rn is 0 if r is between -1 and 1. And of course, if r is 1, so 1 to the power n is just 1, and the sequence is just 1, 1, 1, 1. So its limit would be 1. So either the limit is 0 if r is between -1 and 1. So the limit of this sequence is 0. This sequence is 0. But these two are divergent. There is no limit. The limit will go to infinity. Determine whether the sequence converges or diverges. If it converges, find the limit. Well, what is the limit when n goes to infinity of 2 plus 0.86 to the power n? This is r to the power n, and r is 0.86, and 0.86 is less than 1. So the limit of 0.86 to the power n is 0. So the limit is 2 plus 0, or just 2. So this sequence converges to 2. Now here, how to think of this one? This is 7 to the power negative n. So to find the limit of 3 to the power n times 7 to the power negative n, it would be easier if I write it 3 to the power n over 7 to the power n. This is negative n. If you bring it down, it would be 7 to the power n. And now I notice that I can write it 3 over 7 all to the power n. And now this is r to the power n. And r is 3 over 7, less than 1. So the limit is 0, since r is 3 over 7 and it is less than 1. Here, to find the limit when n goes to infinity of the sequence, if you substitute with n infinity, what would you get? 4 to the power infinity is infinity. 9 to the power infinity is infinity. So you will get infinity over infinity. Here also you will get infinity over infinity. So you have to do something. Here I'll get infinity over infinity. So I cannot find the limit like this. So I have to do something. If you divide by the highest number here, now 4 to the power n, 9 to the power n, which is greater? 9 to the power n is greater. So if I divide the numerator and the denominator by 9 to the power n, okay, what would I get? This is 4 over 9 to the power n, okay? And this is 1 over 9 to the power n. And 9 over to the power n over 9 to the power n is just 1. Now, what is the limit of this? It is 0, because 4 over 9 is less than 1, r. And 1 over 9 is r, less than 1. So the limit is also 0. And the limit of 1 is 1. So the limit would be 0. So the sequence converges. The sequence is convergent. Here also the sequence is convergent. Well, how to deal with this sequence? Well, you have to notice that by the definition of the factorial, which we mentioned in the previous part, so I have 2n minus 1 factorial in the numerator. And in the denominator, you can notice that 2n plus 1 is greater than 2n minus 1. So we said that the definition of the factorial, what is n factorial? It is n times n minus 1 times n minus 2, and so on, until you reach 3 to 1. Okay. For example, if you have 7 factorial, what would be 7 factorial? 7 times 6 times 5 times 4 times 3. What if I write 5 factorial? Would it be correct? Yeah, whenever you want to stop, just put the factorial, because 5 factorial is 5 times 4 times 3 times 2 times 1. So 2n plus 1, I will write it 2n plus 1 times subtract 1, because n minus 1, we subtract 1. So 2n times subtract 1, 2n minus 1. Oh, I have 2n minus 1 here, so I'll stop here. And I put a factorial. Okay, so I can cancel this with this, and an would be 2n plus 1 times 2n. So now it is easy to find the limit. What is the limit when n goes to infinity of 1 over 2n plus 1 times 2n infinity times infinity is infinity, 1 over infinity is 0. So this sequence converges to 0. Now, the last point in this section, when you find the limit and uh, replace n by infinity, you get len infinity, which is infinity because len goes like this. So infinity over infinity. What to do when you have infinity over infinity? Well, if it is r to the power n, you can do what we did here. That's good. But there is no r here to the power n. So what to do? I can use L'Hopital's theorem. And L'Hopital's theorem, we studied L'Hopital's theorem in Calculus 1. And what does it say? It says that limits of f of x over g of x when x approaches anything, a or infinity or whatever, is equal to limit f prime of f of x over g prime of f of x if this limit is of the form infinity over infinity or 0 over 0. So that's L'Hopital's theorem. But L'Hopital's theorem works for functions because you will find the derivative, and we find the derivative of a continuous function. But here, this is discrete, not continuous. The sequence, discrete numbers. So what to do? We mentioned that if you have the limit of the function, then the limit of the sequence would be similar. So let us talk about the function f of x equals ln x over x. And let me find the limit when x approaches infinity of this function. Ln infinity over infinity, it will be infinity over infinity. Since it's infinity over infinity, I can use L'Hopital's rule. And whenever we use L'Hopital's rule, we write h here to tell him that I'm going to use L'Hopital's rule. So the derivative of ln x is 1 over x, and derivative of x is 1. Now, this would be 1 over x. And now when I replace x by infinity, 1 over infinity is 0. So the limit of ln x over x when x approaches infinity is 0. So the limit of ln n over n when n approaches infinity is also 0, and the sequence is convergent. Determine whether the sequence converges or diverges. If converges, find the limits. Well, I'll find the limit immediately. If I find the limit here, look, ln infinity over ln infinity, it will be infinity over infinity. So I consider the function f of x equals ln x over ln 2x. And I start finding the limit when x approaches infinity of this function. Well, ln infinity over infinity, I will have infinity over infinity. So I will use L'Hopital's rule. So it would be limit when x approaches infinity of the derivative of ln x is 1 over x. And the derivative of ln 2x is 1 over 2x times the derivative of 2x, which is 2. So actually it is also 1 over x. So 1 over x over 1 over x is 1. So this is actually limit 1 when x approaches infinity, which is 1. So the limit of ln n over ln 2n or ln 2n when n approaches infinity is 1, and the sequence converges. Here, if you replace n by infinity, you will have infinity squared, which is infinity. E to the power negative infinity is 0. Remember, this is ex. When x goes to negative infinity, ex goes to 0. So a to the power negative infinity is 0. Well, infinity times 0 is an indeterminate form. Okay, the indeterminate forms are infinity times 0 and infinity over infinity, of course, 0 over 0. But we have a way to deal with infinity over infinity and 0 over 0. But what to do when we have infinity times 0? Well, when we have infinity times 0, I change it to infinity over infinity or 0 over 0. And I have to work, remember, with functions. So f of x would be x squared e to the power negative x. And now let me find the limit when x approaches infinity of x squared times e to the power negative x. But this would be infinity over 0. But if you write it limits when x approaches infinity, this is x squared e to the power negative x. If you bring it down and write it e to the power x, now if you replace x with infinity, you have infinity over infinity. So you can use L'Hopital's rule. Derivative of x squared is 2x over ex. Replace x with infinity, infinity over infinity. I use L'Hopital's rule again. Derivative of 2x is 2, derivative of ex is ex. Now when x is infinity, notice e to the power infinity is infinity from the graph. So 2 over infinity is 0. So the limit of n squared e negative n when n goes to infinity would be also 0, and this sequence would be convergent. Now here, if I replace n by infinity, len infinity is infinity, minus len infinity is infinity. I'll have infinity minus infinity. Infinity minus infinity is also an indeterminate form. But here I can write it len n plus 1 over n, because the properties of len, properties of logarithm says that len u over v is len u minus len v. So I have len u minus len v. I can write it len u over v. And now we can find the limit of len n plus 1 over n when n goes to infinity. Remember, what did we do? We let the limit n plus 1 over n. But here we have n over n because the highest power. So n over n is 1, limit 1 is 1, so we have len 1, and len 1 is 0. So this sequence converges to 0. Similar question, okay? You just write it len 2n squared plus 1 over n squared plus 1 and find the limit. It would be len 2. It will go to len 2, similarly like 48 exactly. If I replace n by infinity here, 2 over infinity is 0. So I'll have 1 to the power infinity. And 1 to the power infinity is an indeterminate form. And the way to deal with 1 to the power infinity, we have to deal with functions first. So f of x or y, I'll call it y, equals 1 plus 2 over x to the power x. I need to find the limit of this function when x approaches infinity. But this will give me 1 to the power infinity. How to deal with this? I apply len to both sides. So len y would be len 1 plus 2 over x to the power x. And because of the properties of the logarithmic functions, I have a property that says also len u to the power r is r times len u. So if r is a power of u, you can bring it out. So I can bring the x here down, and I will have len 1 plus 2 over x. And now I will find the limit of ln y when x approaches infinity, okay? And this would be the limit of x len 1 plus 2 over x. And now when I replace x by infinity, I will get infinity times. 2 over infinity is 0. 1 plus 0 is 1. Len 1 is 0. So it would be infinity times 0. And we knew what to do with infinity times 0. We have to write it infinity over infinity or 0 over 0. This means I take the x below. So I write it x to the power negative 1 or 1 over x. And now, if I replace x by infinity, this would be 1 over x, 1 over infinity 0, and this would be ln 1 0, so it would be 0 over 0. 0 over 0, I can use L'Hopital's rule. Find the derivative of the numerator. The derivative of ln is 1 over 1 plus 2 over x times the derivative of 2 over x, which is negative 2 over x square, over the derivative of 1 over x, which is negative 1 over x square. Well, negative, this one, if you want, you can write it negative 1 over x square times 2. To see that, I can cancel these two together, and I will have limit 2 times 1 over 1 plus 2 over x. And now if you replace x by infinity, 2 over infinity is 0, and the answer would be 2 over 1, which is 2. So ln y goes to 2. But I need y, not ln y. So if I raise both sides to the base e, so e to the power ln y, which is y, will go to e square. So the limit of 1 plus 2 over n to the power n when n goes to infinity is e square, and the sequence is convergent. Here also, if I replace n with infinity, I will have infinity to the power 1 over infinity, which is 0. Infinity over 0 is an indeterminate form, and you have to use L'Hopital. So I write f of x or y equals x to the power 1 over x. This is the way to deal with infinity to the power 0, 1 to the power infinity. Okay, you have to do it like this. You have to apply ln to both sides. And then the 1 over x would be here. Okay, and now you find the limit of ln y when x goes to infinity. Or you find the limit of 1 over x ln x. And now you see that 1 over infinity is 0. It is 0 times ln infinity, which is infinity, 0 times infinity. So you try to write it. If you write it ln x over x, it would be infinity over infinity. And now you can use L'Hopital's rule. Derivative of ln x is 1 over x, and derivative of x is 1. So actually, this is limit 1 over x when x approaches infinity. And that's 0. 1 over infinity is 0. So ln y goes to 0. So y goes to e to the power 0, which is 1. So limit n to the power 1 over n when n approaches infinity is 1, and the sequence is convergent. The last example about this point is this sequence. If I replace n by infinity, I will have ln infinity, which is infinity, infinity square, infinity over infinity. So what to do? Infinity over infinity, I work with functions. I make it a function, ln x to the power 2 over x. And I find limit ln x to the power 2 over x. I'll have infinity over infinity. So I can immediately use L'Hopital. The derivative of ln x to the power 2 using the chain rule is 2 times ln x to the power 1 times the derivative of ln x, which is 1 over x. Derivative of x in the denominator is 1. So I have limit when x approaches infinity of 2 ln x over x. All right. And when I replace x by infinity, I'll have infinity over infinity. So I use L'Hopital's again. Derivative of ln x is 1 over x. And derivative of x is 1. So 2 over infinity is 0. So limit ln n to the power 2 over n when n approaches infinity is 0 and the sequence is convergent. I'll stop here and continue the last part in another video.